Good morning. I guess I think it's good to say something. I mean, first, probably you've noticed our TA finally secure the exam. Okay, it will be in Thursday night, 1 hour exam. If you have legitimate reason to be absent, let me know. We can arrange another makeup centralized again on another day, but only if you have let us know in advance. And of course, if a medical emergency, of course, we are able to accommodate that. But otherwise, if only for reason that other than emergency, I mean, you have to have approval in advance that to allow you to make up. Otherwise, makeup will not be allowed. So that was the first thing. So the goal today is to finish this set of slide, okay, and sample this distribution, right? I mean, just okay. Forgot to remind you that I think the assignment will be due because we've done the assignment 1, so assignment 2 will be due next week. You have 7 days more to do it, okay? Just only have 7 questions, so make sure you do at least 1 question a day, then you'll be fine, okay? But you shouldn't. I mean, shouldn't expect you do more than 5 to 10 minutes if you know the material, right? But it's not asking a lot. So there are 2 things, and I'm asking the TA to review my quiz. So probably the quiz for this topic should be released later. So once we done the next chapter, the estimation, probably we'll give you the another assignment, but it's not there yet. I mean, because we haven't finished this topic, okay? So let us briefly review what we are doing because we'll finish this chapter as a goal, and hopefully to start with something estimation. But the goal is to finish this part, which is a foundation the rest of the semester. So what is this chapter about? This chapter is about, as you can see, it's a sampling distribution. The reason being that we are collecting data, and we notice the data we collect is not something you know before you collect it, right? And what you collect, we will model it as a random process, a random variable. Say, if you want to collect data, say whether people would like to come to morning class and or they prefer afternoon class, right? And you would ask people in CHK, and then the way you do is to, of course, talk to everyone, right? In CHK, that would be easiest. But if not, then you're trying to pick up some people, right? Then the way you pick up usually is random, right? It's not going to be deterministic, right? And you don't know in advance who you talk to, then it would mean that who you get and what data you got is a random variable. And for random variable, you would have a distribution, right? You have a big P or big F, right? And in that case, that is what we're about, right? So a reminder, the population is the thing we want to study. We want to draw conclusion on. And very often, we don't have data for all of them because of operational reason. You can't ask everybody. Or logistic reason, it's very costly to do it. Or computation reason, it's very costly to compute all the data. And data availability, you don't really got those data, right? So there's a lot of reason, even you have that or some privacy reason, even you are the company, you own the whole market, no one's allowed to touch the thing, right? Suppose you are the, say, you control data for Twitter or Facebook or Instagram, right? The data you have is so much, you can't really analyze all of them. or there's some privacy reason you can't access all of them, right? There's no one is able to control all the data, right? Because become the weakest link in the system. So what you end up with is a sample, which is a subset of population. And because we want our data, later you see, to be representative sample means that the sample should look very much like population, right? Otherwise, it doesn't tell us about the population. And that means to do so, you will be involved doing some random draw out of that. And that means that the sample, will be a random sample. It's not a fixed sample, it's a random sample. And random sample imply you have a distribution. And just a terminology, right? The underlying population would have a relative frequency F, okay? And you will have a population mean and population variance. And remember, these are numbers, right? Population mean and variance are number. You don't know it, but potentially, if you know it, they're numbers, okay? And you have observation from that's called sample, and random sample is a random draw, okay? And the random draw, because it's random, so the P function or the F function will follow the relative frequency, right? So, and you will have the same mean and variance, right? The expectation with the population mean, right? The variance with that, okay? And we write this capital letter. And simple random sample is easy to do, easy to calculate, but very difficult to realize in the real world, because you have to make sure that everyone is equally likely to be picked up, and choosing one guy doesn't change the other, right? For many reasons, it's very difficult to do, right? So you go to a particular location to collect data, or use particular channel like online or offline, then you would omit many channels unless you randomize the channel in a way that everyone is equally likely to pick up, right? So that is not that easy to operate, but in our calculation, we will have that, and we hope, right, the data we are using is have a good, it's not too much different from this one, okay? And so in our class, we assume simple random sample, which means that they same mu, which is same expectation, same variance, still covariances. Okay, and we define in the last class what is statistics, which is the meaning of this class, right? Statistical analysis for business decision, right? So what's statistics? Statistics is a function of a sample, and since we're talking about random sample, right? So that will be a function of random sample, means is function of random variable, right? And function of random variable is a variable, right? As a random variable, right? Because function means that you have some way to calculate, right? Once the uncertainty realize, you collect the data, then you know the number, then a function is the way that to transform the number you get, right, through the random variable, right, to the numbers. And usually, this statistic is a dimension reduction tools, something like sample mean and sample variance, right? It's just like you output that as the way to simplify your data, and turn out that these numbers are very meaningful. As we see next week, sample mean is very useful to estimate the population mean, and sample variance is very useful to estimate the population variance. Why we care about that? Of course, we want to know the population. Then the best thing is to know the F, right? How the number distribute, right? The F is contain all the information, but it's very difficult to do so. So we're going for easier route. Look at the mean first and variance. Okay. Of course, you want to know kurtosis, skewness, many other things you want to know. But that is beyond the scope of class. Our class will focus on mean and somewhat variance. Okay. And the way to do next class will convince you sample mean and sample variance are a good guess to the population versions. Okay. So that's why we said the sample mean is the calculation that you just add up all the random variable divided by the sample size, okay? And remember, each observation is coming from random sample, so each observation is each x big capital, letter x1 up to xn is a random variable. So adding random variable divided by n is also a random variable, okay? So the key is to know more about how the sample mean looks like, right? Because sample mean is a random variable. And the first two facts coming from the idea of simple random sample, because simple random sample, each observation have the mean mu, right? And that essentially mean the following. It means the expectation of the sample mean is also mu, right? And because of the independence property, so this becomes sigma square over root n, okay? So this comes from simple random sample, right? If they are not random, the variance is not that simple. You have to consider covariance, right? So that means that when we talk about financial price data, the variance cannot be estimated by this, okay? You have to handle the covariance, and that is you will, if you want to handle that, it will be a one semester course on time series analysis. We'll talk about how the correlation do it. Okay, you can do it in stat department. I think our school also offers that as well. 4,000 classes, so we'll be able to handle that. Okay, but we'll focus on simple random sample. So the variance is very simple. So it's just sigma square over n. I mean, and the next is we will talk about is the case when we have large sample. The reason is being that if you don't make any assumption on how the population distribution looks like, then you can't say too much. Okay. But we know one thing is, luckily, the sample mean will be a bell curve regardless of what the underlying distribution looks like, right? Suppose I want to look at how much people want to pay for say, a room model flip phone from Apple, right? Maybe iFlip, right? And in that case, you want to know the range to pay, right? And you don't know in the population how many people want to pay, right? Maybe a lot of people want to pay for it for a very high price, and maybe many people don't want to pay it, right? I don't know what the shape might be. But if you able to collect a lot of samples, then it must follow a bell curve, right? Why is the true? This is coming from what we call central limit theorem, okay? And second thing would be, if you collect a lot of data, then turn out that the variation is gone, right? Actually, thanks to the second property, when n is very large, there's no variation. When sample size is large enough, you got exactly back the population. Okay, or to be fair, you will be very little variation you got. So you actually discover the truth by having a lot of samples, right? So as many as you want, then more. If you lot, then you don't have too much doubt on the result. Although you don't know exactly where it is, but the difference is so small, you don't have to worry too much. Okay. So that is a law of large number and the central limit theorem, right? So there are two important things to study. Okay. And if you go to math department to study statistics, basically they will spend whole semester to prove different version of this and this. Okay. That is how they understand probability for math, starting from set theory, looking at integral, how to do measurement, and at the end up with this kind of results. Okay. And after that, this we'll talk about today's very important part is our central limit theorem said the following, right? Central theorem said is regardless of x how it looks like, okay, and x bar will be a bell curve, right, with mean mu sigma square for n, right? So this is here is mu and sigma square is here, right? And what we said is in order for this to be meaningful, we have the good guess of this guy. Okay. This is not that easy to get this guy. Okay. And if you don't know, then how to proceed, right? Because unless we know the sigma square, this description is not very useful, right? I know it followed the bell curve, but I don't know what's the variance of this, right? Because I have no idea about this guy, right? Then how can we proceed? Okay. Because you usually maybe you have some idea of mu, but you don't have good idea of sigma squared, right? Sigma squared is more difficult to handle. I mean, of course, we know that we can use the sample variance, which is S, to guess this, right? That's the way, right? Because we don't know, we use this guy, right? But we use this guy, it is not a bell curve anymore. Okay, it's not a bell curve anymore. It looks like a bell, but it will be a little bit fatter bell. So you use a T distribution. That's what we're going to cover. Okay, but for this to hold, you can't have this. You have to assume the underlying is a bell. Okay, let me draw it because this is something we'll talk about today. It's an important concept, so I don't want to miss this part. So here I don't know the shape. Okay, there's X here with mean mu sigma square. You collect data, full sampling. You got an X bar, right, which is a random variable because you collect it. And when n is large, central limit theorem said this is the case, right? Right, this is the case, right? And what I'm doing, where am I? Oh, so central limit theorem said the following, right? And of course, you can do normalization, which imply z is 0, right? The range is 1, right? Z is what? Is X bar over mu over sigma square over n, right? So this is what we have, right? But the problem is I don't know sigma square, right? But I replace it by S, right? So the question is I have X bar minus mu over S over root n. Sorry, this is S over root n, right? Because you divide it by standard deviation, right? So it becomes Z, right? This variance 1, right? So if I replace this by this, okay, what shape I got, okay? The problem is if I have any arbitrary shape, I don't have any conclusion, okay? So what I need would be actually from now on, from this point, okay, when we talk about this is we assume this is a bell curve. If this is a bell curve, then this guy will be Tn minus 1. It's a T distribution with n minus 1 degree of freedom. Okay. So we have to make the assumption, what we call normative assumption, which I'll elaborate a little bit more. This when I make the bell curve assumption, then this will be a T distribution. What's T? It's a bell, but fatter bell. Okay. And when n is 200 or 300 or more, then it's very close to the standard bell. Okay. It's very similar to this one. Okay. So there is not too much harm to replace sigma by S if you are willing to make the assumption that the underlying is a bell curve. Okay. And of course, you would ask the question is, if I'm not willing to make the assumption the underlying is a bell curve, what can I do? Yes, there's still things you can do, but it's beyond the scope of our class. You will require you to some what we call numerical method. You will what we call the Monte Carlo simulation method, bootstrapping method. That would be, of course, way beyond the scope of class, but we will be very happy to assume normal. And we learned that by central limit theorem, a lot of things are normal anyway. So it's not something that is too terrible to assume that. Okay? And that is the, if you want to go further, that would be beyond the scope of class. But that would be, the goal today is to tell you this guy. Okay? So that will be the goal of today. Okay, so don't worry, we'll get into more detail very soon. Okay, but just the goal, that tell the goal today. Okay, and the other part we want to talk about first is if the data we have X is not a continuous like this, right? If what we're going to say is if X underlying data is not continuous, but rather just two numbers, 0 or 1. Okay, that's called binary data, which we will do now. Okay, binary data. Okay, of course. Remember, our central limit theorem doesn't say anything, right? Because any distribution is fine. So you also still get this is a bell curve, right? It's a bell curve. Okay. And what we get, okay? In the binary data, okay, you can calculate the average, right? Which is mu, right? Add up how many one divided by total number of them, right? And the population mean is actually what we call the population proportion. Okay. Why? Because you just add up how many one you have, divide by total of them, is the average, the fraction of people who get one, right? It's the proportion. It's called the sample mean is pi, which is the proportion of people of 1. And the sigma square actually can prove, but I don't have time to show it, but will be always 1 minus this guy. So that means that in this binary data, mean and variance are closely related. Once I know the mean, I know the variance. Okay? Why I talk about this special case? Because this special case implies that the following, right? If this is pi, sample mean, right? This will be pi 1 minus pi over n. Okay? And if you remember, this is, if you take one data out of it, this is a Bernoulli distribution, right? Bernoulli, if you n of them, that's a binomial, okay? And that means that for you to calculate this, once I know pi, I know the variance, I know the shape, okay? So I don't have to rely the t idea. I can keep the bell curve, okay? If I only have binary data. So the bell curve or central limit theorem will still apply very well without a big problem, okay? So that is the main idea, because this is a binomial, so I don't really need central limit theorem, right? Because this is a binomial distribution, okay? And that would allow us to do all the calculation without working on the t, right? So let us get back to the slide. Where's my screen? Okay. So let's get to remind yourself what are they, right? First is we know already the mean of the sample mean is the population mean, right? What does that mean? It means that if you have a population, okay, you got a sample, you calculate sample mean, and you got a sample, you not sample mean. You have hundreds of samples or 100 sample mean. Average of this sample mean will be the population mean. Okay, so it means that if you do allow yourself to repeat the process of getting the sample mean, then you know the population mean. Okay, although each time may be very well different from the mu, but the average of those is getting there. Okay, so I think it's good to give an analog. I don't know you guys like football, but I think that is a good analog there, right? There's a football here, there's football net here, okay? And suppose I have penalty kick, right? And consider blue guy is probably Messi, right? And he's very good, right? So he always hit and get the ball into the net, right? That's no problem, right? So he is very accurate. So every time he hits, he gets his X bar is always mu, right? So he's very accurate. Okay. And people like me is very bad at football, right? This is me. Okay. And this is likely to be Messi, right? Or if some people like CR7, also fine, right? Doesn't really matter. And if me, I'm a terrible football player, so I will be actually unable to hit inside the net, but I may hit here, maybe hit here, sometimes over, right? But my abilities to hit outside the net cannot get inside, but average of this is inside the net, right? And that means that I still get the answer right on average, right? So that is the idea, right? I don't get it right, but average of all of my hit is going to get the net, right? So that it means that I am, in terms of expectation, I'm as good as CR7 or Messi, right? Although I don't get in, right? No time I get in, right? But average of those I get in, right? So I'm still as accurate in terms of expectation, okay? Not I get in, none of the by ball get in the net, right? But on average, I get in the net, right? So that's satisfied, right? The idea, okay? So that's the thing, okay? I hope I understand, right? So this is, you can imagine this is the mu, right? Mu is here, right? I want to guess it, right? And Messi or Cristiano Ronaldo or any favorite football star can get in easily, right? For me, I'm very terrible. I don't know how to kick the ball, and I just always kick outside the net, right? Either I'm too powerful or I'm too weak or doesn't work very well. So I end up in outside here, right? But average is still inside, okay? So that is what I have here, okay? So that means that on average, it's hitting the target, okay? Then later we will see, probably should have time. This is a very important property. It's called unbiasedness. It's on average, you get it right, okay? You don't get it right every single time, maybe wrong every single time, but on average, you get it right, okay? And that is important, right? So this is what it means, right? You have each sample, you do the average, and average of these sample mean is the population mean, right? So we have hope if we're able to repeat ourselves many times in the future, then we're able to get the right answer. So that is the idea, okay? And we have already gone through the example showing you that regardless of that, I mean, you can calculate to show you the mean of or expectation of sample mean is the population mean, right? It's 2. And you increase the sample size from 1 to 2, you still get the 2, right? And if you get to 3 or 4 or more, you still get 2, right? This has been proven, right? And of course, there's a math behind. It's a one-page for math. If you like math, you will find that it's not something difficult to go over. It's just 4 steps of math. But if you hate math, then you can skip it, okay? And the next part, as we said, is the variation right? Because I know on average, right? Remember the picture here, right? Macy always get in, right? So for Macy, he's so good that basically the variation is zero, right? Because always get in the net without problem. But for me, I have large variation, right? So you can imagine Macy is infinity guy, right? Sample is very good. The sample size n to infinity, right? For me, it's very bad. Okay. Right? You can imagine because Macy, why he's so good, why I'm so bad, right? Likely that he do a lot of practice or he's very smart, right? So when n go to infinity, this becomes zero, right? But when n is small, this is large, right? So the reason that you get a smaller variation on the sample mean is just you have a lot of sample, right? Because you get more data and data is likely to around the mean, right? Then the sample mean, right, will be way close, much more closer to the true population mean, right? So it's proportional to the original variance, but inversely proportional. That we know this already, so I don't see there's too much worry about that. And one point is we call the standard deviation of the sample mean will be the standard error, okay, of the mean. Okay, do notice that the standard error of the mean, there's no sample here, right? So that's why the error represent this 5 word. Okay. Now the very next part would be to demonstrate in a model that the variance, right, of the sample mean, right, will be following this, right? Is if you have one observation, then same as before, right? Because there's no changes. And you have two, then you will be this is sigma square over n is 2 here, right? So that's why this formula will be read. Okay, not going to do further, but you can do 3 as well. Okay, and you can imagine the variance as a strength when n go to infinity, so you have law of large number, right? Because you divide it by n, right? You getting smaller and smaller. When very big, then you divide by 100. You have 1,000 to 1,000 when n then actually go to 0, right? So that is the meaning of loss of large number. And the other one we said is central limit theorem is saying that eventually become a bell curve. How you look like this is look like this one. Okay, this one. Okay, what you would get is like this, right? Look at X bar. Okay, when you have one sample there, it's likely 1/3, 1/3, 1/3, right? It's like a flat, right? And if you have two, right, the P will be look like one knife, two knife, three knife, one knife, three knife, right? This is the case of two, right? Look like this guy. And if you do the three, right, you try to plug it out, you look like this. Right? And then you go to four, you'll be something like this as well. Something like this as well. Okay. And you can imagine if you do more, he will be very close to the bell curve. Okay. Although I didn't demonstrate, but you can actually try to do it and then you can show you this is a bell curve there. Okay. And that is actually compound central midfield, right? At the beginning, it's a uniform, right? Each number have equal likely they're being drawn, right? The same number there, right? But at the end, you become a bell curve, right? Even though the beginning is a uniform, right? Because the population only have 3 observation and they have different numbers, right? You see, it's a uniform over 1 to 3. Okay, so that will be the answer there. Okay, and the last class we have gone through this, right? X bar minus mu over sigma over root n is a normal CO1, and this apply when n is more than 35. Okay, and here we end with this example. I want to talk about this again because that is super important, because this is the foundation of what we are doing, right? So at the end, let me do it again, right? So this is mu is 5, okay? Sigma square is 64, okay? And the sample size, n is 100, okay? And we ask what is the probability that the sample mean is no more than 4. So this is the question. All right. And we know that by central limit theorem, okay, it must be the case. Let me draw it here. This guy, okay, is a bell curve, right? With mean mu equal to 5. Okay. This, the bell shape will be sigma square over n, which is 64 over 100. Okay. This is how fat the bell should be. Okay, the variance. And we say no more than 5 or more than 4. The question is simply ask you this, right? 4 is here. You ask this guy, right? And if you look at the SD, right, which is sigma over root n, okay, which is 8 over 10, which is 0.8, right? You just take a square root, this 0.8, right? And you would know, what does that mean? The distance between this is just what? 1, right? 4 minus 5. And 4 minus 5 means the SD is 0.8. So the distance is 1.25 SD, right? Because SD is 0.8 and distance 1. So this means it's 1.25 SD, right? So that means that if you draw this bell curve Z, 0, this is 1.25, and the black is here, right? And how can you calculate that? Left-hand side, standard normal. This is simply what? Norm as this negative 1.25. True. Of course, you can use the Z table, and this will give you the answer. You can try in your Excel that it should give you this number. Okay, it's like 10%. Okay, so that is how you get this number. Is that clear? Is that okay? So I hope, because this is transformation, is you minus the mean over the square root of this guy, right? Is that okay? I hope this is okay. If no question, then I go to the next one, because I think I just might likely stop right here. Okay. No question, then I go to the next one. Is there any question? Okay. If any question, you can ask me in the new reply. I can try to explain further. Okay. So as I said, as we start, the binary thing is like this, right? The binary thing is like this, right? The data is either 0 or 1, right? Either you 1 is yes, 0 is no, right? And then the proportion, which is average, right, is known as pi, and the variance pi times 1 minus pi. You can prove it from the math. I'm not going to show that to you. I think I put it in the slide already. Okay. And if you draw single variable there, that would give you the pi, right? And the mean will be pi, and variance pi 1 minus pi. That is come from the Bernoulli distribution, because you draw a number, draw a guy there, it will be either 0 or 1, right? And how likely you get a 1 is the pi, right? So that is same as above, right? And proof is here, but I don't want to bother you with that. You can have fun here. Okay. And everything would work because we didn't say anything about binary data, right? Any data is fine. So that's why the sample proportion is the sample mean, right? It's adding up. Bunch of 1 and 0 divided by n is the sample proportion. And same, the expectation or proportion will be, the sample proportion will be the population proportion. There's nothing new there, right? And what's new there is because of the sigma square equal to pi, 1 minus pi, okay? That means that when we do the central limit theorem, our model will be a little bit interesting, because you will see we replace this guy, right, by this, okay? So it means that if I have knowledge about the mean, which is the population proportion, I can easily apply central limit theorem, okay, without worry about the sigma square, right? Before we worry about that, right? But we don't worry too much, okay, about that, okay? And when we have the general case n is more than 30, this is a good approximation. Then you ask, when is a good approximation? It will be n pi, or n times 1 minus pi is more than 5. That is usually satisfied in most of your application, unless you're talking about where rare event pi is very small, right? When pi is very big, right? Say pi is at least say 0.1, for example, right? You only need 5 sample, right? So this would apply even very small, right? Unless you're thinking pi is like 0.001, something like that, right? If pi is at the minimal, looking about 10%, right? Then you don't have to worry too much about the data, right? Any data you got is almost likely you work. Okay. Now the next thing is what we do after the break, okay, will be the part we mentioned, right? We don't know the sigma, okay? So what to do, right? You will be doing, as I said in the beginning, okay, which we'll cover later after the break, is it's as good if I have sigma, right? Sometimes you do have good estimation, but many of the time you don't, right? Right? Sometimes you have, but sometimes you don't, right? And probably you ask, how can I have a good sigma, right? It's the sample variance, right? The sample variance you can estimate very well, then you don't have problem, right? But what happens if you don't, right? And if you don't, you have to make other assumption, which is assume the underlying is like the bell curve. Once you're willing to do that, we know the sample mean will follow a bell style, but a flatter bell is T distribution. Okay, so everything would work by replacing the sigma by the sample variance. Okay, but at the cost of two things. One is you have to make the underlying is a bell. Second, this would be a T. Okay, that's a two thing you have to add if you don't know sigma. Okay, and that would be something I want to say before the break. Okay, let's a break of 15 minutes, and then in the meantime, we just do you reply, and then we come back to this uh the stuff. Okay, so there's a break of you reply. So I will appreciate if you ask me because I think we are getting into the substantial version of our course. Okay, so please feel free to let me know if you have any question or issues. So I guess we can slowly continue, look at how well we are doing these days. So what is the relation between p hat, p pi, p hat, or whatever? Okay. So what is it? Do I have p hat here? I don't think I use p hat anywhere, but I can explain a little bit what's hat. Actually, we'll do it in the next set of slides. So let me quickly get back. So what is pi and p first? Okay. Pi is a proportion number of people. Just basically pi is a number from 0 to 1, right? Suppose you have in the CHK 60% of people like the morning class, right? Then pi is 0.6, 60%. Okay. And say that means that you have 100 people, 60 of them will say yes, and 40 of them say no, right? And that's the pi, right? And what is p? P will be your sample, right? Suppose you pick up 10 people out of the 100, right? And 7 of them say like morning class, then your P is 0.7. Okay. Do you notice pi is not a random variable? Pi is a number, but P is a random variable. It depends on what kind of stuff you got. Okay. And very often, actually in the many textbook, probably I would use in some cases, we will say if you want to estimate pi, then they use this hat, and that actually represent this p, right? Because which we'll clear in the next class is when you put a hat, is the thing you want to guess, okay? And we'll use p to guess this guy. So sometimes the book with the hat will be the version that is the version that you try to guess, right? So that's why in some textbook, right, you would say mu is the population, right? The sample version we use in our class is X bar, right? But in some cases, some book will use mu hat. Okay, but this is to guess this guy, but they're same thing, right? Or sigma square is the population variance, right? And we use S square to do that, right? But some textbook would be saying sigma hat square. Okay, so the hat is sometimes we call the sample counterpart. Okay, it's a sample version. This population, when you get a head, it's a sample version. So there's some textbook that use it, but maybe I use it some of the lecture slides somewhere, but it's not uniform. But this is what it means. I hope I explain clearly. But if not, then ask me again. I hope I clear your query. How do I convince someone who is sick to stop working and take a rest? Has reached midterm and lecture, but insists not sleeping. Oh, so one, okay, convinced. One thing I think is easy to explain as an economist, okay, is you have diminishing productivity, right? So that is the following. Economist, how many number of hours you work, okay? It is a total product, right? Your productivity, right? You look like this, okay? And you pass through the optimal point, so you should get back, right? The more it's not the more you work, the better, right? There's some diminishing there, right? Of course, that is very similar to the Laffer curve, right? If you work 0 time, you get 0, right? If you don't sleep, then you die. You also 0, right? If you work 24 hours, then work quickly, then you just right? Or you don't have anything to do, right? You are too tired, right? So the optimum point depend who you are, right? But at least I think many of us, right, at most it's like 16, right? If you work beyond 16, it's not going to work anyway, right? Because you don't have enough sleep. And many of you would know some of brain cell will die or doesn't replenish very well. Actually, it's not very efficient, right? So actually, you work more than that, it's not going to work, right? You have to get enough sleep, okay? And if you ask me, when I was a high school kid, the first thing I do when I go home is to sleep. Okay, every day, maybe like 3 p.m. in the afternoon. At least I sleep 3 hours, 2 to 3 hours. When I go home, it's very tired, and then I start working. Uh, and um, when I was a primary school kid, I go, but nowadays they don't have this. We have morning school and afternoon school, and I have an afternoon school. That means that I sleep until very late every day. Because nothing to do in the morning, right? Only TV, so there's no YouTube to have fun. And TV has nothing, not until 10 a.m. to 9:30 to 10 a.m. Only half an hour cartoon, and that's it. Okay. Other time it's just very boring TV shows. Okay. So that means that I sleep, right? A lot. So I don't know that help me, but I do actually sleep quite a lot. And I'm tired, so I used to eat a lot of chocolate. Okay. And now I don't know coffee. So this morning I read a article. They said, I mean, coffee used to feed the cow and the pigs, make they work more, feed the cows. I don't know, ox, right? So I don't know. I'm part of that now, but I used don't like coffee. I drink a lot when I was a first year student because uh, I live in the campus when I first year. So every morning I just drink a lot of coffee. But after I get out from the school, the second or third year, I didn't drink too much coffee because I sleep at home. Uh, and but I don't know. Hopefully, don't overwork because it's not increasing. Okay, and the best case is like this. Even the best case scenario look like this. Okay, doesn't seem to be. It's not going to increase a little bit that much. Okay, so doesn't worth to do it because it's a long run game, right? I will always say this actually even to my PhD student. Life is a marathon. Okay, don't burn out at the very beginning. So you guys are very very young. If you harm yourself, then your future is not going to be bright, right? Because uh, your body is the capital of revolution, right? 身體係革命嘅本錢 right? Is the fundamentals of uh, your existence, right? So make sure that you don't overwork, right? The probability that you would earn a lot, right, get a lot of mileage, if you don't have enough sleep, is very little, right? The probability that you go very well is going to be very little. So don't worry of it. Okay. I hope I answered the question. Central Newton basically said the sample will always have normal, but yes, when the sample size is large enough, the sample mean, okay, sample mean is going to be normal. Okay, doesn't say about the variance, whatever. Doesn't say only the sample mean. The sample mean with the bell curve. Okay, that is what it said. Okay. Explain page 33. Oh, last two step means this to this. Anyway, let me do it. So this step, I think is nothing new, but just norm as this negative 1.25 true. So this is this step. How you get that? Oh, because this is normal 564 over 100, right? So that means that this minus 5 over 8 over 10 is normal CO1. right? Because this minus, how to normalize, right? X is normal mu sigma square, then X minus mu over the is normal CO1, right? So you take a square root of this guy as denominator, that's same, right? So that's why you take, this is square root of 64 over 100. That's why I did, right? And now we have 4 here, so just 4 minus that. Okay? Is that okay? Because, is that okay? And this is the step you explain the math going on here, right? Because this is, remember this what? This is saying that 5 is here, right? This is the shape, right? Then you ask how likely is less than 4 here, right? So we just subtract this difference over square root of this. We'll go from the X bar base to the Z, right? Right, negative 1.25. Why? How you change from normal to standard normal, right? It's asking how many standard deviation from the mean, right? And this is the variance is 0.64. That means the standard deviation is 0.8, right? 0.8, then this difference is 1, right? So the SD is 1.25. But this is below, so it's negative 1.25. And this is how we figure that out. Is that okay? So this, nothing new, right? That's, you know how to change from here to here, right? You'll be doing assignment anyway, right? So you should be able to get. But if you still don't get it, I can still keep going over that to make sure that everyone get it right. Is that okay? Is that okay? If you don't, just feel free to ask me. I mean, we are in this small class, right? Don't hesitate. I mean, I will not remember you ask a question, and indeed you actually ask a question. I remember you get a better grade, right? Actually, it's a positive incentive because I remember you. Only thing is you're better off, right? There's only upside. There's no downside. There's no risk, right? If I remember your face, I remember your name, then actually you slowly get a better treatment than otherwise, right? You slowly is not a punishment, right? Anyway, you don't ask, that's okay. I mean, I don't want to force you to ask me question. What is T? Okay, we'll talk about that. T is we will talk about is if we replace, we'll talk about very soon. But the main idea is following. This is normal. It's fine if we know the sigma square, right? But if we don't know this population sigma, I don't know the variance of the population. So this thing doesn't help us, right? Because I don't know how fat is this guy, how thin is this guy, right? I have no idea. Okay. Then this centimeter, I know still the bell, but I don't know this. I cannot talk about probability, right? Because I want to know the probability. I need to know the sigma. How can we do it? And the easiest question is, I don't know sigma, then I use the sample version, right? S, right? Look at data, calculate the sample variance, right? Take a square root and do the same, right? And turn out, unfortunately, the shape of this is not known without knowing the original shape, right? It really depends on original shape. So the center root doesn't apply if you replace it by the S, okay? So what can we do, okay? And the way that we do is to make assumption to make it work, right? Because we don't know, right? The kind of shape. And one thing is, if we willing to make assumption, the underlying is like the green one, the bell curve. Once on the bell curve, reduce the procedure, this become the T distribution, okay? Of course, if you're assuming something else, then you have something shape, different shape, right? But since we know normal is so normal, so we just work on a normal one, okay? That will become a T, okay? So that's the idea. That's a T idea, okay? If you're different shape, then you have different shape, not T, can be anything else, okay? But we limit ourselves to assuming the line is T, so underlying is normal, then end up the sample mean you normalize it, you become a T. Okay, so that's the idea. Okay, and in general, that's all you have. Okay, because you have no idea about sigma, right? So you have to make the assumption of what we call normality, which we'll talk after we finish the U reply response. Okay, so help answer your question, but don't worry, we'll talk about that. Tired? I'm sorry about that. Many midterm. I know, but we don't have midterm, so at least you can't complain my class, right? So should be happy. 9 a.m. is too early. Okay? Yes. But imagine I live in Hong Kong Island, so I spend 1 hour. I have 1 hour before you guys. Okay? And I have to wake up like 6:30 to cook breakfast for my kids. So I am way earlier than you guys. And I taught until 9:30 last night. So I go home like 10:30 and go back and just try to change some slides and make some adjustment before I go to sleep. So I think you guys sleep more than I do. So that's why I have to drink coffee, right? So that's why you don't have to drink coffee, but I have to drink coffee. Otherwise, I fall asleep. But if you think 9 a.m. is too early, then probably you should do more exercise. I recommend that is something very important to do some exercise to keep your mind fresh, to get some. If you don't want to do exercise, the easiest thing to do more deep breath. Actually, very helpful because replenish the oxygen in your brain. Then it's very helpful. So Monday, oh that's bad. No Monday. Okay, it's Friday. It's Friday. We have at least a 2 day off. Okay. Yep. It's cloudy and there's sunny. Yeah, that's right. Sample proportion, yes. When the sample size large enough, sample mean is equal to population mean. That is law of large number. Okay. And central limit theorem mean when the sample size large enough, sample mean look like bell curve. That is central limit theorem. Good. Everything becomes bell curve. Yes, that is true. But not the sample mean, not everything, right? Sample variance, not bell curve. Okay. But sample mean is a bell curve. Central limit theorem applies when sample mean large. That's true. Instead of data of sample, no, just only the sample mean. Okay, the sample mean become bell curve. Okay, not everything because it's not everything become bell curve. Okay, just make sure is there. Okay, property, yes. Okay, that's right. The speed's okay, except one person. I think this person live in the Monday. That's my guess. Maybe I'm wrong. Sorry. Okay, and maybe this is also a Monday person, but it's okay. I don't want to pinpoint anyone, but it's okay. Hopefully it's okay. But I just remind you again, we have TA in this class. Please schedule appointment with her if you have a question. And we should have a tutorial, optional tutorial section soon. I'm asking the another TA to organize it. Then you can ask more questions because I guess you don't want to ask me. That's okay. We have very young, handsome tutorial and have to do tutorial and have a young, beautiful TA lady can help you. Okay. So if you don't want to talk to old generation like me, you have a younger generation talk to you. So it should be fine. Okay. And you're very tired. This is the case. Okay. And since you guys student, let me make a guess. I taught part-time last night, right? As I told you, at night time. They work 8 hours or 10 hours a day and then come to the class. How tired they are. Say, it's an estimation question. Number one, like what you're doing. A. Number two, not much, very similar, uniform. C, maybe, okay, they're actually not that tired because they used to wear tires. So go to school is actually easier because they don't have to go overtime. Okay. Number D is something like, this is more extreme, right? Number D is something like this. Maybe use other color, right? because not very clear. Number D is like this. Okay. Number E is like this. E is the bimodal, right? There's a big mode there, big mode there. What do you think? Who thinks A? A like you guys? No one thinks like you guys. Well, what thinks B? No one thinks uniform. But uniform is the best guess, right? If you don't know, you should guess B, right? Okay, you have some idea. Fine. Number C, who think number C? No one think number C? Okay. Who think number D? Number D. Number D, okay. Who thinks number E? Okay. Turn out the answer is number D is what you see for the part-time student, and E is what you ask the PhD student, the graduate school student. They're actually full-time graduate student, like E. Part-time student is part-time graduate student who look like the D one, increasing. Some people still okay, but most of them are very tired. Okay. So, but if I were you, I would guess the best guess for me would be B, because I don't know. Then it's uniform is the best guess, right? But no one actually, if you don't, no one use central limit theorem, right? No one would say it should be like this. Surprisingly, right? If you believe central limit theorem, that should be something like this, right? But of course, we know that when talk about human, unlikely a bell curve, because people would be pretty much extreme. Okay, but I think that's a good example of what you will see. No. Someone phoned. Oh, yeah. I don't know. I don't know why. There's someone out of Hong Kong keep calling me international phone, but I don't know why. But I never pick up those. Anyway, nothing start with letter N with letter G, NG. I don't know. Is anything start with N and with G? Probably not. Just want to end my midterms. Yeah, hopefully you end your midterm. Well, I guess you only have one question per day, only 7 questions. So I guess if I delay that, then we have to delay other assignment. So if you really need one, you can talk to the TA. The TA may grant you special approval if you explain why you are late, or maybe you're sick or you're some reason. I think we handle this by individual basis. If you really have reason, I think TA is okay to grant you a that extension. But in general, we don't. Okay, unless you have special reason, you are sick or you have some special reason to delay. But because only you do one question per day, right? Because we give like 10 days, 10 or 15 days more than that. So unless a strong reason, I think we shouldn't allow that happen. When is my birthday? In February. It's like 7 days after the Valentine's, wait, after Valentine's, because my son is supposed to born in Valentine's Day, but 2 days delay. So anyway, but why I want to do that? You want to have a happy birthday cake on my face? But I hope you don't. Fun Friday. What is my favorite football team? I don't watch that much football. So I don't really know which team I favor. But when I was kid, I used to watch a World Cup sometime because there's no TV anyway. At that time, people support Brazil, many people, but I really don't. I really don't watch that much football. So I don't really know it that much. My wife likes football, so she would know, can tell you a team. I think she like Spain or whatever. But I myself, I don't know. I don't really care. And my son like playing football, but they don't watch football anyway. So I know no idea. Sorry, this one I have no idea because I don't really watch football. Oh, oh. Sorry about that. Oh, but I did notice when I was kid, there's always on TV, there's a British team, Manchester United. The reason many people like it, not me, but many of my girl classmates put a lot of poster on their book because of David Beckham, right? It's very handsome, very before he married to before they get married, right? He's very handsome. Now maybe still handsome, but he was way much more handsome at that time, right? So maybe at the time many people like Manchester United, but not much for me. So I'm not, unfortunately, a very boring person in life. So unable to tell you too much about personal history or story. But let's go back to here. As we said, it is right. The sample mean will follow a normal, but we don't know this guy, right? So how can we solve this problem? As we said, we try to use this sample variance. Do note with n-1, and we'll talk about why n-1 in the next class, because n-1 is a good guess for the sigma square. Okay, and why it's good? Because what we said is unbiasedness. It's what we said on average. It's getting there. Okay, but if you use n instead of n-1, on average you don't get your football in the goal. Okay, so if you care of unbiasedness, S square is the thing you keep. Okay, but we'll talk about this next class, so don't worry about that. If you're curious, you can check the slide of next week, then you will see. Okay, but we'll talk about that. So be patient, but I already tell you the answer. The answer is now is this. The answer is because this guy is this. That's the reason. Okay, if you calculate many sample, you calculate the sample variance. Okay, average of this sample variance is sigma square. Okay, it means that if you don't divide by n-1, you divide n instead, the average of those sample variance is less than the sigma square we want to guess. Okay, you underestimate if you do the n divide by n. Okay, you divide a bigger number. You should divide a smaller number to get it. Okay, so I hope. But don't worry, I'll talk about this next class. But just in case you wonder, okay. So if I replace this by this, right, that means that our standard error will be look like this. Okay, is our guess of standard error, estimation error like this. Okay, of course the question would be, right, everything is random variable, right? Now this is random variable, right? Before this is sigma, right? Sigma is not random variable, right? We know sigma, but now random variable, right? So two random variable there. Right? This replace this random variable, right? So and what is the shape, right? Two random variable over each other, right? How can you know that? But luckily, in the 1930s, if did a bell, then we know, okay? We know the bell. Is there a bell? Okay, we know. So we will make the assumption what we call normality assumption, right? So we will make the assumption that the population follow a bell curve, okay? And it may or may not hold, okay? And in our model, we just assume that happened. Okay? There's some way to check, but in general, that is okay, not too crazy assumption. We have to start with work with something, okay? And if you violate that, we will use the what we call Monte Carlo bootstrap method. That is, you study in advanced classes, okay? So you can dispense with that, but it's not something we study today, okay? So under this assumption, if there's a bell, the average is also bell, right? So what I mean is just try to draw again, okay? What's normality assumption? Normality assumption means that the population we care is the bell, okay? Mean mu sigma square, okay? And if you draw data from this bell, of course, the sample mean is also bell, right? Remember when we draw a bell, it's a bell, two bell add together, also a bell, right? You add two bell together divided by total minimum of them, still a bell, right? Because you multiply, add, subtract, is also a bell, right? So that's why this is a bell. Okay. It's a bell. Okay. And this is mu, and this is sigma squared over n, right? So this is a bell. Stay. Now, okay. Once we're bell, then okay. And the question would be, okay, this is the bell, right? And you divide this is what? It's called the T distribution. Okay. I'm not going to prove it, but the idea is the following. Okay. I just skip to the math a little bit first, just quickly in case you care. You can solve this guy is a chi-square. And later you will show, sorry, this guy, that's a chi-square, and this guy is standard normal. So that's why I have a normal over chi-square, so you have T. Okay. But I'm not going to talk about this proof in case you wonder that is in the 59 and 60. Okay. But I just use this part because I guess undergrad, no one ever talk about why this is true. Okay. They just give the answer. Okay. If you go to master class, they will understand. You do a proof. Okay. Why you have this. Okay. But instead, I want to focus on application of this. Okay. I have a population that have mean of 5. Okay. That's a normal. Okay. It's a normal. And sample size is 100. Variance is 8. What is 4.5? So what's the question here? Let's do the full screen. Okay. So what do we have here? Okay. What we have here is we have the original data. It's a bell curve. This is what we call normality assumption. Okay. With mean mu is 5. Okay. And sigma square is we don't know. If we know, then we can use central limit theorem. Okay. We can't. So we have no idea. Okay. And next would be the X bar. Okay. X bar would be also 5 here. Okay. And it will be sigma square over n, right? But this guy is not known as well, right? If we know, then we're done, right? But what we know is the data we get has S squared is A. Okay. So it means that the question is asking less than 4.5. Okay, it's this guy. Right? But we don't know sigma square. How can we proceed? Okay. Turn out to be let me use the purple color as well. Okay. T 99, Y99, because of sample size 100. We'll take 1 from that. Okay. And this is 0. Okay. So what we're going to do is you don't know sigma square, you replace by S square over n, right? You don't know sigma square. Okay. And look at this distance. This distance what? This distance is 0.5, right? And you want to measure it by standard, how many standard deviation you have, right? So it's 0.5 over square root of this guy. Okay. What's S square? S square is 8. N is 100. Okay. So the distance is 0.5. So I look at the number here. What this number is 0.5. 5 over square root 8 over 100, right? Because x square root of x 100 is SD, right? Look at how many SD below the mean, right? And this turned out to be, you can do the calculator, is negative 1.768. Okay. And once you check this area is same as this area, right? They're the same. Why the color is not there? The color. This area and this area the same, so the same thing. Okay. Right? Same, right? We want to look at the distance from the center, right? By how many SD? This is a T99. Okay. And that means that I can do the Excel, how to calculate this area, because area on the left, so it's just T dot this negative 1.768. Okay. And 99 is here, 99. True. So that, then you can figure out that is like 4%. Okay. So that's not too much different from the set, right? The only thing is you do the same procedure, but you don't use sigma, you use S. To do this is say how many SD below the mean or above the mean. And you don't check the normal S this, but you use the T this. And then you have to tell them which table you look at. Okay. Because T has many tables. Normal only have one. And T table, which one to check, it just depends on the sample size, -1. Okay. Because you don't check number one table, right? Number one node table is nothing, right? You don't have, you check from the 99 table. Right? Is that clear? Because number one table has no meaning, right? So you check the 99th table there. Okay. So that is how you get the answer. Is that clear? So this is, of course, this is the math behind all the below, but that is what I said, right? Just basically you subtract 5 on both sides and divide by standard deviation. Then you convert this to T99, right? And then T99 is just below. Just basically the graph is actually telling the math down there, okay? But of course, when you do the assignment, you will be reproducing the same thing, okay? Is that okay? Is there any question? Okay. I hope it's okay. Is that okay? Is there any question? So, and there's something called T table, and the T table doesn't give you the probability, but rather it tells you that this is the center probability, tells you the two ends. Okay, so you can't use it to calculate the probability I have already. Okay, so that's why I tell you that in the slide you can only tell the range. Okay, and since in the assignment you can use Excel, then I will ask you the exact solution. But in exam, I don't want you to do this complicated math, right? So you can see my past paper. If I ever ask, I just ask you the Excel function. So as long as you know the Excel function, it should be fine. Okay. So I don't really expect, unless I ask you to come up with the fraction. Usually I don't, right? But you may ask why I would do that. You'll be clear later why you need these two numbers. Okay. You will be use it when we calculate estimation in the next class. Okay. So one minor thing I want to mention is because we rely on normal assumption, right? So we need to check the normality, right? And that means that we need to see if they're normal, right? You want to see, then how can we know? There's some way. First, we know normal is symmetric and kurtosis is slight free. So you can look at the data, look at the sample skewness, is it close to 0? Or look at kurtosis, is it next to 3? Right? It's not different from 3, then you're fine. Okay. Of course, there are something we call the JB test that would also allow you to formally see whether right or wrong, but that's beyond the scope of a class. Or you can look at data, look at histogram of the data, it looks like a bell curve. Okay. If that's the case, then it should be, you can't say you can prove anything, but at least making this assumption has some validity, right? You can never prove it's a normal or not because you never know the population. So there's no way you can prove. But at least the evidence, is it going to be saying that you don't make a crazy assumption? Okay. Okay. So that is something that we have to say. Okay. That was the thing. So since we have some time, let me do another exercise here. Instead of less than 4.5, let's ask a question. More than, say, 5.5. Okay, let's ask this question. Okay, so the question is this: X bar more than 5.5. Okay, and let me show you how to calculate that. Okay, so hopefully that would ease your concern a bit. Okay, let me write down the solution first. Our mu is 5, right? I've sampled 100. My sample variance is 8. Okay, and I'm asking this question: X bar is more than 5.5. Okay, of course, the underlying is normal. Okay, so let me write down this again. X is 5 here. Okay, and sigma square, I don't know, no idea. Okay, and I collect data from sample mean. It's still a 5 here. Right, I don't know. This is the variance sigma square n, but unfortunately, I can't use this fact, right? Because I don't know sigma square, right? So if I know, it's easy, right? Because this is normal, then 5.5, I can just change to standard normal. I can find this area, right? I can just look at how many standard deviation. I know sigma square, this over the square root of this, right? Can convert to the Z space and just calculate, right? There's no problem, right? But the problem is it's not a bell without knowing this. Right? I cannot calculate. So what to do is instead of dividing this guy, you divide the distance by S over root n, right? Because you don't know this, you replace by this guy, right? This you replace, right? Once you replace, you look at how many SD, right? And this number, right? How many SD you have, right? This is, you calculate this number will be T99, 0 is here. Sorry, so I should use other color. Right? So this is T99, 0 is here. Okay. And this one, where is this guy? This is just 0.5 over square root of 8 of 100. Okay. And what's that number? It's 1.76. This number is 1.768. Okay. And we want this area. Okay. And we know the area on the left-hand side. T dot this number 99, true. 1 minus is the answer. Right? So if you want that, The answer will be just T dot this 1.699. True. But this is, remember, this is our left-hand side. So 1 minus is the answer. Okay. So that's will be equal to the answer that we want. Okay. Okay. So good luck for your midterm. I'll see you next week. Hope you're not that tired. Have a good rest. I will stay behind to answer any question you may have.